Good morning. Today we start, I think it's the third lecture on equipment, both in Nano Center of Excellency. And today's lecture, Professor Dražić will show you in the first half basics of focus ion system, and then Jože Buch will introduce you, will demonstrate you how the microscope works. So,
thank you. That's a nice introduction. Dear colleagues, now I have really a difficult task, because my previous lecture was something from the experience of maybe 20 years or something like that. And this will be lecture with the experience again, something like 20, but not years, but days. Because the FIB, or focused ion beam, this machine was installed maybe a month ago, 2 months ago, and in this period there was 2 or 3 broken parts and malfunctioning valves and so on. But still, we have very, very nice machine. It's the second in Slovenia, but with all attachments and possibilities and options, it's definitely the first one. It consists of the scanning electron microscope, which has the best performances, I think, in not just Slovenia, but slightly also around here. So let's start at the beginning. I will talk about FIB, this is company, Helios Nanolab 650. This is the model of this dual beam. Why dual beam? Because indeed we have electrons and ions. So 2 columns, 2 beams. It's bought in the frame of the Center of Excellence in Nanoscience and Nanotechnology. Using FIB you can do, okay, maybe not everything, but a lot of things. You can build something. Okay, this is the University College of London. I count the pillows, there are not so many, but still, the resemblance is quite very good. I do not understand that one here. It must be something with Japanese sense of humor. It's made by a Japanese guy. And those fans of Star Trek, maybe not ladies, but boys, perhaps. This is the smallest Enterprise ship. Dimension is somewhere around 5 microns. And here are 2 examples of not just playing around with FIB, but indeed with the device that worked. This is the Cornell University, and those results are relatively old, maybe 15 years. They make a guitar. Any guitar player here? It's a special type. Can you comment a little bit? Which type of guitar is this? Okay, I forgot. Because the design and the morphology of this guitar, it's really, I don't know who played on this guitar. But it has strings. And those strings vibrate if you put the laser beam on, because the frequencies are somehow combined. And also this xylophone, or I would say nanophone, because xylo is something with wood. This is something with nano materials. So it's really a machine that can do a lot of things. And the main idea is, of course, that with fine movements, fine tunings, you can sculpture the things you want to do. So you have ion beams, which is traveling around on your surface and digging a hole. Okay, if you increase the energy, it's not the artistic work anymore, it's more powerful. And of course you can increase even more. And I think that if we put the complete all energy and current on our FIB, it's something like that. You can really destroy your sample and perform really, really big holes inside. But let's see what we will talking about today. Just a few facts about the instrumentation, detectors, ion column, ion source, gas injector system, so on. Some basics about interaction of ions and solid material, and some application. And of course, this most interesting part will be at the end, when you are all welcome to join colleague Jože, which will demonstrate the things that I will explain previously. And on the side, beside the microscope. So the ion source, we have to produce ions. Those ions should have relatively high energy, so it should be heavy. And normally, nowadays, are used gallium. Why gallium? Because gallium is a funny metal. It has melting point very low. Something around, I think, 30 degrees centigrade. So you need really small amount of energy to make it liquid. And this is the basic idea of the source. You have very sharp tip. At the end, it's so-called, physicists would maybe know better, so-called Taylor cone. And at the end, you apply some voltage, high voltage, in the range of 1 to 10 kilovolts. And those atoms at the top of this cone are ionized. They lose electrons, they became the gallium plus, and you just accelerate those ions down to the column. And this is a practical ion source from FIB. The lifetime of such ion source is somewhere around 1,000 hours, 1,200 hours. So if you use extensively this machine, it should be changed twice per year, for instance, so once to twice per year. Schematically, again, this source, this is so-called liquid metal ion source. There are also other sources. The system or the machines, the FIB is first mentioned or practically designed somewhere in late 70s, 76, 78. In 80s, there was, you could already bought some relatively good machines, and nowadays they are really perfect with high resolution and so on. And this is the practical ion column, where you have this liquid metal ion source, this extractor cap. So you extract the ions from that tip. You have first lens, you have aperture, you have some quadrupoles and octopoles here. I will explain later on why we do need them. Some blanking plates so that we can blank the beam. We do not want to have a beam, we just blank, we just curve the beam somewhere here. And we have second lens. First lens, the function of first lens to make beam parallel, and the second lens to make beam focused. And of course, this focus should be on the center. Lenses. In transmission electron microscope and scanning electron microscope, if you remember, the lenses are electromagnetical. So you have some current running through this electromagnetic lens, magnetic field inside, the electrons are trying to spin around and so on. Here, because we have much higher mass than the electron, we are using the electrostatic or electrical. So we have just electrical field, and the positive, of course, ion will curve, the trajectory will pertain to the negative electron. This is more in detail, such a column, but practically the same, maybe just nicely shown. We have some additional apertures, depends on what current of the ions we want to have here. As I said before, the first lens should make parallel beam, and that octopole here is just, again, some electrostatic lenses, but divided in 8 segments, where we where we change or where we improve the stigmatism, so that we really, at the end, we should have really focused, nice, nice circle rounded beam. And the lower part, lower octopole, is needed for just scanning. So scanning means this beam is just performing lines, scanning in that direction. As an integral part of the ion column, normally is also the multi-channel plate, which is used as the detector for getting the signal from our sample. So, just a brief explanation of the detectors. Maybe I will start or just mention the so-called ET detector, Everhard Torni, just some name. It originated from scanning electron microscopy, just a combination of Faraday cage, of some scintillator, light guide, and photomultiplier. We collect electrons from all around here with this positively charged Faraday cup. Those electrons are striking some scintillator. That means material that emit light. Electron comes in, out goes light in visible spectrum. Normally nowadays they are used YAG, so yttrium aluminum garnet material. Then we need some piece of plastic, optically very good, light guide, because the function of this is to suppress the electrons. Maybe some electrons could pass this scintillator, not to ruin the photomultiplier, because one high energetic electrons could destroy your photomultiplier. It's a very sensitive piece of this detector, and this light that is emitted in this part here, the scintillator is just multiplied with this photomultiplier. And at the end, we get the signal. If we have a small amount of electrons here, the signal will be low. If we have a large amount of electrons, the signal will be high. That's the whole idea. Another idea or another possibility is so-called multi-channel plates, where this is just schematically drawn. We have some kind of channels, again some potential, so that charged particles, so not just electrons, but also the ions could be detected with these detectors. We just switch the polarity. If you want to attract electrons, we need plus. If you want to attract the ions, positively charged ions, we need minus. Here is the practical such detector, and this is the scheme of one channel. There's a gradient of the voltage around here, and using one quant of primary radiation, we end with a lot of electrons. And because this is a parallel channels, you see this one here, this inside part, the sensitivity of such detectors could be relatively high. So with that detector ET, we can measure just electrons, and with that one we can measure simultaneously, or depending on the voltage, plus or minus, we can measure electrons or ions. Okay, we have in this microscope we have another possibility, and this is so-called scanning transmission mode. So that very thin samples like prepared for the transmission electron microscope, a special sample holder. This is the path of the electrons, and this is retractable. So when we need it, we put it in. When we do not need it, we put it out. Detector for electrons. And here's the one example of bright field and dark field imaging with such type of detectors. What is characteristic? Definitely in bright field, the hole where there is no sample is bright, and in dark field is dark. In dark field, we are just collecting those electrons that are diffracted due to different processes. I'll not go into the detail about that. And here are two additional equipment, which is normally also connected with focused ion beam. Due to the lack of time, of course, in this lecture I'm concentrating just on the ions. Because I think everybody already heard about electrons and scanning electron microscopy and so on. Most of you practically working with scanning electron microscopy, so I somehow imagine that it would be more interesting to talk about ion column, ions and so on. So another part of this complete system is gas injection system. This system ends with very, very tiny capillary, which is, I think, some 100 microns or something like that at the end. And certain gas, it depends on what type of material we want to use, it's coming out from here. Okay, it's not blowing, but the partial pressure here, I think it's at least 2 orders of magnitude worse than around here. And why this use? This is used for the deposition. We will see later on how indeed we can perform this process. And we have also the micro manipulator. This is again very, very complicated device which could be moved mechanical. Okay, at the end we have mechanical movements which is realized, of course, with piezo transducers and quite a complicated computer-supported system. We can move this part, this very point of this micro manipulator, in the range of few tenths of nanometers. Why is this used? We will also see later on. So just an example of this. So now, just briefly about the principle of the photosynthesis. We modify the surface using positively charged ions, in our case gallium ions. There are some approaches nowadays for the last few years where also helium, it's a much more complicated machine, where helium ions are used and they can achieve also much better resolution than helium. But for normal work, still gallium is a lot of energy and you can proceed, or you can do your job relatively quite quickly. So we have accelerated positive ions of gallium, and at the surface we have few type of interaction. Elastic interaction, which is displacement, sputtering, defect formation, ion flotation, and so on, and inelastic, energy is lost. In that case, where the secondary electrons are formed, secondary ions, X-ray, photons, and so on. As I showed before, if we move that beam, we can do surface patterning. We can put some patterns on the surface, we can draw something at the surface. So sputtering is just moving or removal of the material by elastic collision between ions and target ions, or our sample. And this process we need few hundred electron volts of energy. Typically, focused ion beam works at 30 kilo electron volts, so there's a lot of energy, but it could go down to 1 kilo or even less. I think our goes to 500. Still, we have enough energy to be on this regime. It should be more than 5 kilo, and okay, these are not could be around 1 kilo. And sputtering occurs, we have collision cascade. Next slide, we'll see example of such cascade. But what is important is that most ejected those atoms or ions, secondary ions, are just from the top few atomic layers. And this is the idea of, if you remember one method, SIMS, secondary ion mass spectroscopy, which is it's a surface technique. It's very sensitive just for the surface, and also the detection limit is very low. Few atoms per, I don't know, you can detect it. Good. And this is the example of such collision cascade. So one primary gallium ion comes to our surface. It move one atom from its position, and of course change trajectory at some angle, and still have some energy, can move it another one, and so on, till the end. Till the end, this one lost complete energy, and it's implanted. It's there, sitting there. And you can determine it with energy dispersive X-ray spectrometry. There is high concentration of gallium in all materials that were cut using the FIB. Cascade means that all other atoms or ions can do the same thing. And at the end, you might get some sputtered species, sputtered atoms, and some electrons. Secondary electrons and secondary ions. What is the depth? So in scanning, if you remember, the scanning electron microscope, this famous volume. So you might have here 5 or even less, 1 nanometer sized electron beam. But if you are using 20 kilo electron volts of energy, at the end you will get a signal from 2 micrometers. Depends which type of signal. The worst resolution is X-rays. So here, slightly better are backscatter electrons, even better are secondary electrons, but still, doesn't matter the diameter of the incident electrons, you always have much larger interaction volume. And this interaction volume is, of course, also very important and interesting here. So these are some calculations, Monte Carlo calculation of one trajectory of just one gallium atom. It goes from here with the surface up to here, which is 50 nano, something like 20-25 nanometers. And these are the complete cascade. So not just the gallium, but also the intrinsic material, intrinsic ion that are inside. If you multiply this with, I don't know, a few tens, 100 for instance, we see that the estimated volume where our information comes, or where we damage our material, is still somewhere in the order of 20, 30, 50 nanometers. It's not so bad. Using 30 kilovolts. If we would lower the energy, also this volume would be much smaller. Or if we change the material, that was aluminium and now we have gold. And we see that this interaction volume is much smaller, 20 in the similar case. So what could be also interesting is the effect of energy and angle on the projected range of this volume that interacts. And we can see here for gallium, and as a material that we use for sputtering or for examination is silicon, that's that one here. So at 30 kilo electron volts, it's also with our microscope, which is the maximum energy, we are somewhere around 25 up to 30 using, again, silicon. So in gold it will be something like that, in lower Z material slightly larger. But if we lower the energy, also this interaction volume would be much smaller. Why is this important? Imagine that you want to prepare TEM, means for transmission electron microscope, a lamella assembly. So if you use the high energy electrons, you will end with the material that suffer somehow, could be destroyed, could be amorphized. In the range of 20 nanometers, it's much too much. For transmission electron microscope, maybe we can survive with 1, 2, 3 nanometers maximum. So we should be in that range here. Definitely below 5 keV, maybe on 2, 3, or 1. Angle of incidence, that means just the angle between the sample and 90 degrees, 180, which of course it's parallel, does not mean, okay, something like that. But this angle and the sputtering yield. What does it mean, sputtering yield? You can just imagine how much atom you move with one ion. And we see that the maximum is something like that. Of course, at 90 degrees again, it's lowering down, but the maximum is here around 70, 80 degrees of the angle. And again, depends on the sputtering yield of different material. Silicon is very low, and with zinc, it's much higher. So that the rule of thumb means 1 nanometer of destroyed area, of amorphous area, corresponds practically to 1 kilo electron volt, which is really true. Okay, now let's go to some parameters that are important for imaging. Yield of secondary electrons depends on the material. Okay, here we can have secondary electron yield, it's gamma, and it's that one for different energies. Let's take this one, 30 kilo electron volts. And we see that the yield is lowering when the atomic number is increasing. So for the low Z material, oxygen, carbon, and so on, it will be much higher production of secondary electrons than for the high material. This is good information. Why? Because we can most probably easily see oxide layer on some grain boundaries. We'll see the example later on. At the same time, spattering here, that means how much ions, secondary ions we are producing. It's Y, it's that one here. And this one is rising. It's higher if the Z gets higher. So, taking into account those two quantities, we can imagine what type of images or what type of contrast we should use to get the information that we want. And of course, the penetration depth, we have already said, it's relatively low. Here are some examples on what else influence on the signal, on the intensity of the signal. The influence on the orientation, crystal orientation, it's very important. Here is one so-called channeling effect. What does it mean? If you have the orientation, okay, the gallium are coming from that part, from up to down, and if you have here some kind of channels, this gallium can penetrate quite deeply inside the material. If you have some orientation, but this is enough just to tilt your sample, your crystal for 45 degrees. In one case you have channeling, in that case, you know, depends on the structure, of course, and on the tilt of your sample. For instance, this one here, you have no channeling. That means that most of gallium ions are interactive matter, and there are a lot of more signal, or secondary ion, or secondary electrons. It's also important the Z, or the atomic number. So if you have heavier elements, gold, platinum, comparing to aluminium or carbon and so on, at higher Z materials we will have higher signals. And also it's important the angle, what we explained before, this functionless laser. If in this part, the angle could be practically 90, and this part is 0. So from this part we'll get more information, more electrons and ions than from that part here. Once more, this is a study how this is just electron channeling, how this channeling influences the yield. Yield of, this case now we have gold atoms and gallium ions. And these are the orientation of this gold. Gold is cubic. And in one case, this is 001. This is that. We have relatively low yield, low signal. Why? Due to channeling. Because those gallium can penetrate inside and they do not produce secondary ions, secondary electrons at the surface where we can measure. And when we orient this in this range where practically no channeling can occur, the yield, or the number of atoms, secondary ions, which are produced are much higher. Again, it's lower in some specific orientations, some specific zone axes, and the highest is around here, where practically no channel is present in this material. And again here, this is 1, 1, 0, means from here we went to that position, just 45 degrees, and 45 degrees we change the orientation of our crystal, and we get much different signal, much different yield, between much different things. But can this be used for some application? Yeah. This is so-called channeling. If you have channeling, the signal is dark because there are not much electrons and ions, and here is no channeling. And in that case, you can see every grain, it has its own brightness, its own contrast. This means that this one has no channeling, and this one has very high channeling. And even you can see that the depth of the penetration, efficiency, is different due to this channeling. You might get very nice images using this channeling. And here's some example. These are electrons, normally secondary electrons, and these are ion-induced secondary electrons. So in both cases you measure the electrons, but in that case you also use electrons for the signal, and here you use ions, but measure electrons. And you see really nice images due to the channel. Okay, if I just repeat once more, we have different detectors, and we have different imaging modes using these detectors, and all those modes depends on this basic physics that I showed you in last few transparencies. There are also possibility to put inside such a machine also mass spectrometer, as I said before, and you get really good analytical machine. Okay, how we can use this focused ion beam? Three basic areas that we are using. It's imaging, etching, and deposition. Imaging we already described, what type of signals and what is the influence of different parameters on the signal. We use this multi-channel plate as a detector, and we image the surface. We can increase the current of beams of ion beam, and we can drill a hole. This is etching. We can deep etch the material, or we can put some gas which decomposed under the beam and decomposed in some metallic thin film, deposited thin film, and these are just the volatile organic remainings of this reaction. Maybe just some examples of all these different areas. We can perform a regular cross-section, nice sandwich structure. We just dig a hole here, and using electrons or ions, we can see nice images. Of course, this is stolen from the internet, from the website of the factory, FIB, and this is made here at the institute this last time, 1 month or 2 months. Not just imaging, we can also do some tomography or 3D reconstruction. We can cut a layer, like here. We can identify as a signal, as an image, or even using X-rays, we can determine the chemical composition. Then we sliced away another slice and another slice. We get so-called such data cubes from every such a slice, and at the end we can reconstruct the three-dimensional real sample here, like the distribution of, I think it was copper and iron or aluminum, something like that. This is one example. Example of the deposition. Here is just one schematic more. So first we deposit or absorb absorb the gas molecules, which contain some platinum, iron, platinum, gold, tungsten, and so on, and some organic radicals around. They are in the gas form, using focused ions or even electrons. We decompose this material, and this tungsten, or platinum, or gold remains at the top of our sample, and those species that are volatile and made due to this decomposition just goes in the vacuum system. Some example of the deposition of electrodes. Some nanotube, 4-point measuring. Those lines of platinum were deposited. This is just the zoom of this part here. These are some large electrodes that we can use for measuring. Roger will show you his own experiment. He was doing mostly these deposition experiments in last month. Again, one such example of deposition. We can even build some nano actuators or some nano devices, like this absolute pressure sensor, which is just deposited in such arcade way. So we end here, we have some hole with fixed pressure down here, and depending on the outside pressure, this material is compressing or elongating. And measuring, I don't know, optical properties or electrical properties, we can measure the pressure inside that. And as the last example, what focused ion beams could be very useful is the transmission X-ray microscope sample preparation. Those of you that are dealing with transmission X-ray microscope, you know how important it is to get good, nice samples. Without sample, you can do nothing. And nowadays the problem is to prepare a sample at specific area. It's practically impossible because you are using techniques that you are within plus minus few millimeters, but if you want to exactly make a sample from this part or some other parts, you can use then it. Okay, I can show you a movie, and it's better. Hope it will work. Yeah. Shall I do double? Okay. So the first act is the deposition of platinum. You see, platinum is deposited. Of course, the time scale here is much exaggerated. You need maybe a few minutes for this one. So you peel up a part of platinum, and then you drill a hole here. You turn around the sample, drill a hole around here. Okay? So you end with such very roughly made lamella. You cut it here and there. You see, it's fixed just on this part. This is platinum. You can use then fine thinning, fine milling on this part and another part. You can thin it. You can not down to extreme, because this next part could resemble on Greek tragedy, because this is the most critical part. You see, the size of this, it's very small. This is micro-manipulated. And you should bring this micro-manipulated just few tens of or hundreds of nanometers, and you weld it here, you cut it there, and you get lamella. Very easy, huh? We did not get any good lamella. So
how long does it take to?
1 hour.
Only.
Yeah, depends on. Okay, and then of course you have to fix this lamella somewhere. You have some special sample holders. Fix it inside. Again, the next step, very crucial, to put this lamella here. And this here, you see, this big tube is this gas system, this gas injection system. where you will put again some small part of platinum. Here you cut there, and you have lamella fixed on the TM sample folder. Of course, this lamella is still very thick and with very large amount of amorphous material. Okay, maybe the final or semi-final act, now you have to really do fine thinning of your lamella. Still, I would say it's maybe something like 2 microns, definitely too thick. But if you can go down to 50, 70 nanometers, maybe like this one here, and especially again using low energy, so that you will not end with amorphous lamella. At the end, you see here, some areas are really, really thin. And that's it, the end of the happy end. Okay, but of course the company or the producers of FIB, they are saying, no problem, 1 hour, 2 hours. You can, overnight you can do 5 to 10 samples. Okay, then you speak with really guys that are doing FIB, that are preparing, they say, okay, if you prepare 1 good lamella per day, this is really, you're really experienced. So it depends on what you want, because you can end with such type of transmission electron microscope sample. This is 5 nanometer, that means here is 20 nanometers of amorphous layer using 30 kilo electron volts. You can end with something like 2, with 5, or even practically without a very, very small amount of amorphous inside at the top of your sample. So you can imagine that this is what you want, or even better. Okay, I think I came to the end. This is our microscope, or our dual beam, our FIB. During the installation, so not everything is finished yet. At the moment, it's, we removed some nice parts of the machine because we have some problems with valves and we have to manually open and close valves. But it will be definitely, it's a complicated machine, and hopefully it will be fixed in next weeks. I hope still this year. These are just briefly the specifications, if somebody is interested, but you can find this on internet. Electron beam, this is the scanning electron microscope, it's really good resolution. Also at 1 kilovolt, it's below 1 nanometer, and this is due to the monochromator. So this machine, or this column, has monochromator at the top, just below the electron source, which even improves the resolution at lower energies. Ranges at from 20 volts to 30 kilovolts. We are still talking about electron beam. And the landing voltages for electron beam 20 to 30, and for ion beam half to 30 kiloelectron volts. Probe current, you see it's from 0.8 picoamperes to 26 nanoamperes. It's really huge range of the electron, also of the ion beam. So in that case you are really polishing and using very, very artistic approach, and in that case you are using dynamite, or these big cranes. We have 4 different gas injection systems. We can deposit platinum, insulator, which is based on silica, silicon oxide, gold, and we also have enhanced etching using iodine, so that we can improve etching in the factor 10 or 20, just due to chemical reaction of the surface atom with iodine. Of course, we have this in situ sample lift out, charge neutralizer, and resolution for ion beam is around 4, depends on how we measure. 2.5 nanometers, comparing to that is much worse, but still you can get nice images to magnification of up to 20,000, 50,000. We have these types of detectors. backscatter, secondary, ET detector, infrared camera. We have this eyes detector for this detector for the ions, retractable detector for bright field, dark field, for scanning transmission electromicroscopy, and beam current measurement. There are also some special software like Auto TM. So you just press the button and he, in 1 or 2 hours, he will make completely automatically lamella. In reality, it means that after 5 minutes it stopped working because there's some problem, corrupted something, and so on. So we are. Of course, if you do this on uniform, ideal sample like surface of the silicon, it could be done. But if you're using the practical sample with a lot of pores, some other features there, then this automatically recognition system somehow fails. You have to do it manually, but no problem. You can put 5 samples inside, 1, 2, 3, 4, 5, also the middle. It's a very huge stage, chamber. And this is the image from the part of the sample. This is electron column, ion column, one detector, another detector, third. This is the EDS system. And you can imagine a lot of this very tiny system for gas injection, and micromanipulators should be somewhere like here. And those things are moving in and out. And if you, it's very easily to destroy this inner part of the FIB relatively very quickly. It could be quite expensive and so on. So if you will work on this machine, it's really very important to follow the procedures, to be very careful, because this is not like a computer. You can practically do no harm. Just reset it. These mechanical parts could be quite problematic. Some of our work, as I said, Jože did some electrical measurements on, what was this, molybdenum nitrate, or I guess nanotube. They performed some very funny structure. We play a little bit with lamella. Okay, we end at that part. It stopped already automatically. It stopped after that. You see this very rough surface of our sample. Okay. You know the Devil's Tower in I think it's Wyoming. Yeah, they succeeded very. But this one is very nice for climbing, and I guess they try to do more polish to this. But experience will help in all these areas. Okay, thank you for your attention, and to be continued. It means when we learned a lot of more, when we had much more experience, then I guess we can also do another lecture or another presentation, what it could be done. I think it could be done much more than I described. And now you're welcome, invited to join Jože, who will show you in vivo for the next hour.